Assalamu alaikum, Chem 20. So as promised, this is going to be a re-recording of the VSEPR notes class. And we're going to go through the theory, do a couple of examples, and see essentially how the VSEPR theory for drawing molecules, more specifically covalent compounds, how it all really works. So when we say VSEPR, what VSEPR is it's an acronym, okay? And an acronym is just an abbreviation of a bunch of words coming together. So this VSEPR stands for valence shell, whoops, let me just write that a little bit better here. The valence shell electron pair, because you can have lone pairs. Now in Chem 20 we distinguish between bonding electrons and lone pairs. So valence shell electron pair repulsion. And of course, this is all just a theory, which means that we haven't completely proven this yet beyond reasonable doubt. So the valence shell electron pair repulsion theory. And what this states is that it recognizes, we could say, recognizes, and I'll write that a little bit better here, hold on. Recognizes that electrons will be repelled by one another while simultaneously being attracted to the nucleus, because there's a whole collection of protons in the nucleus. So the fact that electrons are locked in place by the repulsion, the electrostatic repulsion towards each other, and electrostatic attraction to the nucleus, they kind of move in fixed distances, and these fixed points create 3D shapes. And these 3D shapes, so these fixed points, as I said, create 3D shapes, and these shapes are what we call VSEPR diagrams of compounds. And so to decide on the specific shape or diagram, we consider two things. And these two things are the number of bonds and the number of lone pairs. And when we're talking about the number of lone pairs, it's really just the center atom only, okay? So yeah, center atom only. And although there may be lone pairs on the non-center atoms, they are not going to affect or help us really determine the ultimate shape of the molecule. So the way it works is we use this VSEPR theory chart. And when we zoom in on this chart here, you see that the center atoms are represented by the letter A, and the non-center atoms are represented by the letter X. And so we look at two things. We look at the number of electron lone pairs, and we look at the number of bonds, and that's what the BP stands for. So when we look at a tetrahedral shape, if you look at the types of electron pairs under that column, it says that this atom will be a tetrahedral shape if we count 0 lone pairs and 4 bond pairs, or 4 bonds, okay, around the center atom after we've done the Lewis structure. And so when we do this, okay, we see that the VSEPR diagram, if I try to see if I could zoom in even more, whoops, I zoomed out. I guess this is as much as I can zoom in. CH4, for example, okay, you see that if we were to complete the Lewis dot diagram, we would have 4 bonds around the carbon, so each hydrogen is bonded to the carbon. That's 4 bond pairs, or 4 BP, and there would be 0 lone pairs around the carbon. And so the ultimate shape would look like the VSEPR diagram that you see towards the right. Okay? And the same is true with all the other shapes. Let's say I have a compound that has 3 bonds and 1 lone pair, like NH3, for example. then it's going to be a bipyramidal shape. Okay, or pyramidal, it depends on how you want to say it. And so, again, after drawing the Lewis structure, we would see that the VSEPR diagram looks like this with an angle of 107.3 degrees. Now, you will not be expected to draw all the angles. There's only one case where we draw the angles. But this is what we do. We draw the Lewis structures first, then we count the number of bonds, count the number of lone pairs, use this chart to help us figure out what shape it's going to be, and then we simply just draw it, and we draw it as best as we can. And so the general VSEPR strategy is going to be as follows. The first thing that you do is you draw the complete Lewis structure. So I'll just, Lewis structure of the compound, and that would include all the double bonds with the, the lone pairs and everything included, the full step process. Once you've drawn the Lewis structure, the next thing would be to count the number of bonds in the chart. Before we called bonds bond pairs, but it's the same thing. Count number of bonds and number of lone pairs. And again, remember, this is going to be for the center atom only. Okay, so center only. So you should not be counting this for all the other non-center atoms. Once we've done that, then your third step is just to use the chart to determine the VSEPR shape. Okay, so let's do our first example here and see how this process really looks like when we translate it to an actual problem. So our first example is going to be carbon tetrachloride. So we're going to draw the Lewis diagram step by step here in case people still needed a review on that. So the first thing for the Lewis diagram is we're going to draw all the Lewis dot diagrams of each element, and I'll just, since all the chlorines are going to be the same, I'll just draw the chlorines once. And this chlorine, remember that this would be multiplied by 4 because there'd be 4 of them here. So the next step would be to count the total valence electrons. And so to do that, we're going to add up all the valence electrons from the Lewis dot diagrams that we see. So it'd be 4 from carbon plus 7 times 4 from your chlorine. And in total, this would be 32 valence electrons. Okay, let me just write that 3 a little better. All right, so once we've calculated the total valence electrons, the next step is using the one with the most single bonds or bonding electrons. That'll go in the middle, and everything else is going to single bond around it. So in this case, that would be the carbon. It has 4 bonding electrons, whereas chlorine only has 1. So we're going to put carbon in the middle, and we're going to bond everything else around it here. Next, once we've done that, we're going to distribute all the 32 electrons around the carbon tetrachloride. So we're going to go carbon, I'll redraw it over here. And then using a different color, we're going to add in the electrons. And so remember that each bond counts as 2. So we already have 2, 4, 6, 8 from the bonds. And then we'll fill up each one until it is full, and then move on to the next atom. Once we distribute all our electrodes, we have 32. That would leave none around the carbon. And so the next part here is to calculate the forwable charge. Why carbon here would have a forwable charge of 4 valence electrons minus the number of dots that you would see, which in this case is 0, minus the number of bonds that it makes, which is 4. And so carbon here, 4 minus 0 minus 4 would be a total forwable charge of 0. Okay. Now for each chlorine, Normally you would do them all, but I'm just going to calculate one of them since they all are going to be identical in this case. So we're going to go 7 valence electrons minus 6 dots, and this is for all chlorines. So we can write chlorines 1 to 4, okay, all of them here, minus the number of bonds that each one is experiencing is 1. And so in total, 7 minus 6 minus 1 gives us a formal charge of 0. And so there are no reasons to make any double bonds here or triple bonds, as all the formal charges for all the elements are 0. So now this brings us to step 1 of the VSEPR, which is now we have the Lewis dot diagram. And I'm going to redraw it here, and we'll do this a lot quicker. And once that diagram is complete, which we completed beforehand, now what we're going to do is count the number of bonds for the center atom and the number of lone pairs. So we see that the center atom in terms of bonds, we'll do this in yellow color, has 1, 2, 3, 4. So we're going to write here, and this would be step 2. This would be 4 bonds. And then lone pairs, carbon has none. Now I know you're looking at the chlorines and seeing that every one of them, right, has 3 lone pairs each. But they're not important to us when we're trying to determine the VSEPR shape. Only the carbon is, and this one has 0 lone pairs. And so what I want you to do at this point is pause the video, take a look at the chart that I have posted on the Google Classroom, and see if this is going to be either a tetrahedral, an angular, a linear, a bipyramidal, or a trigonal planar. And these are the shapes that we are going to deal with in Chem 20. So pause the video, look and see which of the shapes have 4 bonds and 0 lone pairs, and then come back to it and try and see if we can draw the shape on our own. All right, so by now you would have seen that the 4 bonds and 0 lone pairs leads to what we call a tetrahedral shape. And that would be the A, or the center atom, in the middle looking like this. And everything else is bonded around the carbon in a very specific fashion. The dotted line over here just indicates that it's in behind, because these are 3D shapes, right? So this is in behind. The triangle here indicates that it is forward. And then, of course, we have another bond at the side. And so your carbon tetrachloride looks something like this. Okay? And this is called a tetrahedral shape. Now, every time we draw a VSEPR diagram, I want you to write the shape down, because not all of us are very good at drawing. And it might be hard for me to see what it is that you tried to draw, but if you write the shape name down, then I am able to know that you understand the main idea and the concepts. All right, another example that we'll do here is carbon dioxide. So the first thing that we need is the Lewis structure. So we'll spend a couple of minutes doing that first. So we're going to draw the Lewis dot diagrams of each one first here. And now this one I'll just do ×2, since all the oxygens are going to be the same. Once we've done this, we're going to calculate the total valence electrodes. The third thing that we're going to do is decide which one goes in the middle, and that's determined by the most bonding electrons. In this case, it's carbon, and we're going to single bond all the non-center atoms around it. And the fourth step that we're going to do here is distribute all 16 electrodes and calculate the formal charges. calculating the formal charges of each would make this 6 minus 6 minus 1, which gives us a formal charge of -1. And the same would be for the other oxygen. And then finally for the carbon, this would be 4 minus 0 dots minus 2 bonds, which is a charge of +2. And so to make everything 0, these two are going to give a lone pair, which means they're going to form a bond. And finally, your structure will look like this. And this is step 5. All right, and now that we have our final Lewis structure with all the dots, this 5th step here really, when it comes to VSEPR, becomes step 1. And so for VSEPR, the first step is getting this Lewis diagram. And so we're going to draw that, and then we're going to count, right, the number of bonds and lone pairs, but not just in the total atom, of course, around the center atom only. So when we do that, we see that carbon, which is the center atom, makes 2 bonds. Now, people said, well, why 2 bonds? I can actually see 4 here. We're going to underline this and write a little note. And this will be a rule. And that is in VSEPR, triple and double bonds count as 1 bond. And this is never going to be changed. There are no exceptions to this rule. The reason why this is the case, and this is a little bit advanced for Chem 20, this is more like university chemistry, but electrons end up being waves. And when electrons are waves, if you look at them like a wave instead of an actual particle, a double bond is really just like a wave that is double the size. And a triple bond is really just a wave that is triple the size. It's not an actual particle. But for now, for us to have some sort of working knowledge, we're just going to consider that a double and a triple bond count as 1 bond. So in this case, counting these doubles as 1, we're going to say that carbon has 2 bonds. So 2 bonds. And the number of lone pairs, well, I know that each oxygen has 2 lone pairs each. But when we talk about VSEPR, we're not concerned about the lone pairs of the non-center atoms. We want the lone pairs of the center atoms only. So that being said, carbon has no lone pairs. So when we record our information here, this would be 0 lone pairs. So then using this criteria of 2 bonds and 0 lone pairs, I want you to pause the video, go once again to that chart that I posted on the Google Classroom, and see which shape fits this criteria. So by now, after seeing the chart, we would see that the final VSEPR shape is what we call a linear shape. And in VSEPR, we can draw the bonds, double bonds like this, or since a double bond is really just a single bond, you can also draw it like this. Either way is fine, but remember what I want to see written is that this is a linear shape.